Um, Hello everyone. I'm going to be talking about 8085 microprocessor, and here I refer to this 8085 microprocessor as also like uh, Samurai Semiconductor, which is a weird name by the way. I know that it's a weird name, but I mentioned it in such a way. I'm trying to use the word samurai here because samurais are known for uh, doing a lot of things, and similarly in this case, semiconductor is also doing a lot of things. And here I've also given a quote for your reading, and it says that semiconductor is like the uh, brain of the human or whatever. So it is like it is used for controlling the uh, the whole computer apparatus and all. Okay.
Hi guys, I'm Aditya. Today I'm going to tell you all about the history of 8085 microprocessor. You may look at this diagram and think, is this how the 8085 processor look like? No, this is a picture from ChatGPT. But let's look into a deep dive of 8085 processor and let us understand its history, components, pin diagram, and all about the address bus. And let's look at some examples how 8085 processor runs. Before we delve into the 8085 processor history, we should also look at some of the predecessor. The 8085 process predecessor was the 8080 microprocessor, which was also developed by the Intel company. 8080 processor was a very incredible processor at that time and was used in personal computers and wide range of computer systems. But the Intel thought that they could improve and upgrade the 8080 processor. So that's why the 8085 project came into the being. So let's look at the 8085 processor. Uh, the 8085 processor was introduced by the Intel company in 1976. It was far more advanced than the 8080 processor. It was cost effective and has many features which the 8080 lacked. While developing the 8080 processor, 8085 processor, the engineers kept 3 points in the mind to enhance its performance, reliability, and also keep the compatibility with 8080 because it was widely used at that time. They also tried to improve some of the aspects of the 8080 processor, such as the power consumption and some of the features like interrupt systems which were lacking at that time. If you look at this diagram, this is the 8085 processor and this is some of the internal looking. This is the 8080 processor and its pin diagram. Now let's look at some technical specifications of the 8085 processor. 8085 processor is an 8-bit processor. Now what do you mean by 8-bit here? 8-bit means that it can process up to 8 bits of data, or the data bus size of the microprocessor is of 8 bits. 8085 processor is a 40-pin dual in-line package. It has 16-bit address bus, allowing it to address up to 64 KB. Now, how did we arrive up to 64 KB number here? Let's look into some of the max. 16-bit address bus so that it could access up to address location of 2 to the power 16. Now, 2 to the power 16 could be written as 2 to the power 6 into 2 to the power 10 bits. 2 to the power 10 bits is nothing but KB, and 2 to the power 6 is 64. So, 64 KB. And 8085 processor is operated at a clock speed of 3 megahertz. Now, this 3 megahertz is because of a quartz crystal's vibration. Its natural frequency is 6 megahertz, but due to its strain and stress, it will give us the frequency of 3 megahertz. Uh, 8085 processor also has retained its capability with 8080 instruction set, but also includes some additional instructions like SIM and RAM. 8085 processor uses a single plus 5 power volt supply. Some of the application of the 8085 processor is that at that time the consumer electronics widely used the 8085 processor. It was included in the calculators, personal computers, home appliances. It is also used in the systems like Silhouette ZX80 and ZX81. It was also used in the educational tools due to its simplicity and ease of understanding. 8085 became a popular choice for educational purposes. It was used in many educational kits laboratory to teach microprocessor architecture and programming. Still now we are using some parts of some of the 8085 processor in like in traffic signals, some parts of the mobile phones, and etc. etc. In industrial controls, the 8085 processor was also used in industrial control system due to its reliability, cost effectiveness. It's also helped us in automating and controlling machinery and processes.
the whole computer apparatus and all. Okay. So here I'll be discussing about the visual. Here in the slide, I'm going to be talking about visual representations of the pins in the microprocessor. As you can see here, the pin one starts from the left top left corner of the microprocessor, and it just goes down. And as we go down, we increase number by one. So one, two, three, so on till 20. We end up having 20, and then we go to the right. And after going to right, we take the the number of the pin is 21 here, and then 22. And as we go up, we increment the pin number by one. So here we increment by one over and over again till we get 40. So there are from this figure we can see that there are like 40 pins in this particular microprocessor, which means that intuitively you can understand that it can do a lot of stuff by itself. And one major prerequisite before entering this particular concept of microprocessor is that microprocessors cannot store memory inside the microprocessor. Okay, this point will come again as we talk about the functions of various pins in the microprocessor. Okay, the anatomy and significance of each pin in the microprocessor. So as we can see here, we start with the pins number 1 and 2. These pins 1 and 2 are for controlling the clock cycle in the semiconductor. Clock is basically kind of kind of electric pulse, which is used to turn on and off certain types of what do we say components in a particular microprocessor. The clock speed defines how well a computer can multitask uh, from a given set of a lot of functions. I mean, it can do a lot of things. Okay, these pins are for clock frequency adjustment, and here in this slide it is not mentioned, but the clock frequency adjustment happens by piezoelectric material, which is inside the semiconductor. Okay, that is extra knowledge. Okay, anyways, and now we know that for any particular any particular electrical appliance, we need electricity to pass through. We need a little bit of voltage for a particular electrical appliance to work. Uh, may it be as simple as what do we say, some motor or whatever. We might even take LED. We need a voltage for simplest of the simplest electrical appliances to work. So similarly for this particular microprocessor also, we need we need voltage. So there should be a potential difference between 2 points in this particular circuit. So the pins to which the voltages are given for a particular microprocessor to work. Uh, so we so as we can see here, we're having pin number 20 and pin number 40. These diagonally separated pins are there, no? So in those diagonally separated pins, there is a potential difference. And due to that potential difference, the whole microprocessor works perfectly. Okay. So, and the pin at the pin 20, which is right over here, VSS, as you can see in the bottom, uh, there is, we have attached the ground voltage to this particular pin. And to pin number 40, we have attached 5 volts of 5 volts of plus 5 volts of what do we say potential difference. And due to this particular potential difference between these two pins, the whole thing works. Okay. So the pins are for the interrupts, which is a very important feature for a computer. Suppose let us say you're in the middle of a particular work, and suddenly the building in which you are there starts what do we say is under the fire. Let us say. So if it is under the fire, you are supposed to save yourself no matter how urgent the work is. You have to save yourself. So in order to save yourself, you just suddenly run out of the building. So similar way, in similar ways, computer also sometimes has to execute certain what do we say, certain types of uh, operations suddenly, and that too, sometimes it might need to even compromise the work it is which it is presently doing in order to do some other work. And the signal for that some other work kind of thing comes from interrupt. As you can see, the name itself has a word interrupt. Interrupt. The interrupts are there to interrupt whatever the computer or the microprocessor is doing currently. So as we can see here, there are different types of interrupts. So as we go, if we look at the diagram over again, here we see trap interrupt, which is at the pin number 6, trap 7.5 interrupt, which is at the pin 7, trap 6.5 interrupt, which is at the pin number 8, and RST 5.5 interrupt, which is at pin number 9, INTR, this is also kind of interrupt, and INTA, which is at the pin number 11, this is also kind of interrupt. These two, INTR and INTA, are somewhat special kind of interrupts, and those are having lesser priority. And RST 7.5, RST 6.5, RST 5.5 are also types of interrupts, which are like which are placed in moderate priority order. And in those RST 7.5, 6.5, 5.5, we have RST 7.5 to have the highest priority in the RST 7.5, 6.5, and 5.5. And then we have 6.5 as the priority, like what priority, by priority, I mean the priority in which the message, the interruption can happen. That is what I mean by the priority. So in the RST 5.5, this is also, this has the least priority among RST 7.5, 6.5, and 5.5. And trap, as you can see here, trap interrupt has the highest, what do we say, highest priority among all the interrupts. Uh, so that is that is about trap. And trap is a non-maskable input. That is, uh, suppose let us say there is a signal which is passing through trap. The signal which is passing through trap cannot be ignored. That is what is meant by non-maskable input. And by maskable input, we might guess the definition to be the interrupt whose warnings can be ignored to some extent. Okay, analogy. So a whistle from a kitchen helps us to divert our attention to the meals which is being cooked. So suppose let us say there is some sort of an appliance, uh, and it has a whistle kind of thing. So if there were no whistle, it might so happen that we might forget about us cooking the dish or whatever, and it could potentially burn our house. So in a similar way, we need trap interrupt, which is really really important. So computer cannot miss the trap signal. So these are the lesser important signals. RST in this particular thing does means restart. Analogy. Suppose RST signals are like the notification from social media platform. Most of the times you may respond to the notification, but it is completely in your mind that you could you could just open the notification, or you could just choose to ignore it. That is the kind of that is the kind of analogy which I'm trying to use to explain what RST is. Okay. Hopefully the thing is clear. And okay, interrupt-based pins. These INTR and INTA pins are used to acknowledge external requests made by external requests. By external requests, I mean that so what I'm this particular microprocessor is like uh, is a particular chip, I can say, and there could be another components which could be attached to this particular microprocessor, including some things like keyboard or mouse, or maybe uh, some other thing. And for outputs, we may use something like monitor and all. Okay, so that is for external appliances. Uh, Interrupt-based pins, INTR and INTA, are used to acknowledge external requests. So, suppose let us say we are moving a mouse. So in order to acknowledge the external request made by this particular mouse or a particular keyboard or any other kind of thing, we need to have these INTA and INTR pins. So INTR is a polite external interrupt request, and INTA is a processor way of acknowledging and accepting the request. So let us just see the diagram to make it clear. So I have a mouse. From mouse, there has to go to we have to give microprocessor a signal that the cursor has to move in a particular direction or whatever. So INTA, INTR gives the particular signal to the microprocessor, and INTA uh, makes sure that the whole request gets accepted completely properly. Okay, that is about INTA and INTR. So INTA is at pin 11 and INTR is at pin 10. So INTA is at pin 11 and INTR is at pin 10. In INTR, the input is taken, the microprocessor receives input via INTR. R stands for request and A stands for acknowledgement. So here, this particular microprocessor is acknowledging the fact that it has received signals. Okay. Pins 4 and pins 4 and 5, which are SOD and SID, are there to give and take serial inputs respectively. S in the SOD and SID stands for serial, and O stands for output, and I stands for input. So serial output and serial input are there in SOD and SID. So suppose let us say we as humans, suppose we are we respond to each other by talking to each other, and we listen to other humans to understand what they are saying. Similarly, computer has to have a way in which it responds to other external data. Here in this particular slip, right? In INTR and INTA, we are responding to the signals made by the particular external device. And in the by using pins 4 and 5, we are we are giving and taking serial inputs, uh, pure data, uh, pure data from the computer to the external devices. Uh, that is how pins 4 and 5 work. Pin 37 is there to maintain the sync between microprocessor and external appliances. So there has to be a sync between keyboard and mouse and monitor and everything that is going on in a computer, or else it'll just be a complete mess. So in order to maintain that particular sync, pin 37 is used. Similarly, to maintain sync and reset the external appliances, to reset the external appliances whenever needed, we need to use pin number 3. Okay. Pins related to data transfer. We were talking about pure data transfer in pins 4 and 5, which are for like SOD and SID. Yeah, SOD and SID, pins 4 and 5. So, uh, pure data transfer, we're also having some other pins. There are 8 pins on each side of the microprocessor. So there is like one pair of eight 8 pins which carry data, pure data. So pins 12 to 19 of the 8085 microprocessor makes up the data bus. Uh, makes up the data bus. Okay, I don't think this changed. Okay, okay. So these are bidirectional pins. So we can't say that the data is flowing from one side to the other only, or this it is only coming from the microprocessor and it is reaching the external appliances. We can't say that. We uh, we must understand that the pins from 12 to 19 are bidirectional pins, which might cause chaos if not handled properly. So for that particular thing, we're having another pin called pin number 30 in order to manage what is happening in 12 to 19, which will discuss about in quite a which will discuss about few slides later. Okay, anyways, so data bus. D0 to D7. Okay. So as you can see here, we're having AD0, AD1, AD2, AD3, AD4, AD5, AD6, AD7, right? D0, D1, D2, D3, D4, D5, D6, D7. These are like D is data bus. That is all we have to learn from this data bus. These pins, 12th being the 12th pin number 12 being the least significant bit and 19th being the most significant bit, handle 8-bit data during the communication between processor and external memory or input-output devices. The microprocessor sends or receives 8-bit data via these lines. So microprocessor, the whole paragraph is self-explanatory. So the microprocessor receives 8-bit data pulses all at once, with 12th pin receiving the least significant bit of the eight bits of data, and 19th one is the most significant bit of those 8 bits of data, which is coming from one side of the microprocessor. We'll talk about the other side of the microprocessor as well. So, in simpler terms, think of these pins as road on which the data travels on. Whenever we think of bus, we think of a huge vehicle which is carrying a lot of people to different and distant places. Similarly, in computer, it is not the people who are getting traveled from one place to another, or one location to another. It is the data which is getting traveled from one place to another, or one location to another. To be more specific. Okay. Here, the location is inside a particular appliance, like HDD, in which uh, we use blades of what do we say, alternating magnetic fields to store data, and we use a certain type of special scanner to uh, decode the hard drive. Okay. ALE, which is address latch enable pin. So as I said before, the 12th to 19th pins are bidirectional in nature, and they have to be managed a bit more carefully for us to be for us to not end up in chaos. Okay, so how does a computer know if the 12 to 19th bit is receiving the data or getting the data, or what's happening basically? So how to manage the chaos in the 12th to 19th? So in the ALE, which is address latch enable, uh, pin located on the pin 30 of the 8085 microprocessor, function of ALE, address latch enable, is a signal. It is a signal that 8085 uses to differentiate between the address and data multiplexed AD0 to AD7 pins, which is 12 to 19. AD0 to AD7, sorry, AD0 to AD7 from 12 to 19. Okay. Mm. So mm, that is what happens in the 12 to 19th pin. Let us just also learn about what happens in the other side of the microprocessor, quite literally. So in the pins related to data transfer to, before in the previous slide I wrote pins related to data transfer one, in which I signify one pair of 8 bits which goes through the microprocessor. And here I'm talking about the second pair of data 8 bits which goes through the microprocessor. And this time it is not two-way connection like in the previous case. It is just like one-way connection. The functionality of the pins 21 to 28. As we had 12 to 19, now we are having 21 to 28. These pins A to A15 represent the upper byte of the 16-bit address. So the one which we are talking about in the left side of the microprocessor, it stores the lower byte of the 16-bit address, and the one which is located on the right side of the 8085 microprocessor, is carrying the upper byte of the 16-bit address. So 8085 can address 64 kilobytes of memory, which requires 16-bit address. We can do the math. 16-bit address, 16-bit address corresponds to 2 power 16 different types of locations, and 2 power 16 could be represented as 64 kilobytes, where 1 kilo is, I think, 1 kilobyte, so 64 kilobytes, right? So 2 power 6 and 1 kilo is 2 power 10 bytes of the, uh, 2 power 10 bytes in memory. So that is how we do the math and get this number of 64 kilobytes of memory. So in order to find data in the external memory, as I said before that microprocessor does not have any memory component on its own. It just passes the addresses in order to access the memory in the external devices, which could be some other hard drive or STD or whatever. Uh, we'll need to just send the addresses and not the, we can't just directly send the memory properly. And all. Okay, pin number 31. When this pin is activated, this pin gets activated when it is set to zero. WR bar should be, I don't think the bar is properly visible in this particular slide, but WR bar is the actual way in which we talk about this particular function, or sorry, this particular pin. So when this pin is activated, that is when when low signal is being passed through right pin, it tells the system that microprocessor is ready to write data to memory. So similarly, when this similarly when the read pin is set to zero, when the low signal passes through the read pin, the microprocessor knows that it has to read data, and that is how that is how what happen. That is how microprocessor knows when to read data or when to write data. Okay, pin 33 of the microprocessor, uh, of the 8085 microprocessor, is a status signal pin. It is a part of a signal system control signals which indicate the type of operation which is being performed during a machine cycle. During a machine cycle, we have four stages, which is de- fetch, decode, execute, and store. And pin S0 is uh, is made for us to know what what stage uh, suppose let us say a program is being executed in the microprocessor. So in order for us to know what stage at what stage the microprocessor is uh, at what stage microprocessor is doing its job. So for that we have pin number 33. Okay, and hold pin, which is pin number 38. This is an input pin which indicates a request from another device like DMA controller. DMA controller is another kind of special device, we can say, to take over the address and data buses. When 8085 receives this request, it will release the buses after completing its current instruction. Hold, okay, and HLDA. This is an input pin that signals to the requesting device that 8085 has acknowledged the hold request. If the particular thing, if this if 8085 microprocessor acknowledges the hold signal, HLDA will release. So there is an output pin that signals requesting the external device. So this is the way in which external devices will know that 8085 microprocessor is ready to do whatever it is supposed to do in this particular uh, while the DMA controller is active. So you can see an analogy over here. And
Hello guys, now let's understand the components of the 8085 processor. This is the internal diagram of the 8085 processor. Let us study each and every component of this processor. The accumulator. The accumulator is a register. So what is a register? Register is a memory storing component in a 8085 processor, and a register is made up of many flip-flops. An accumulator is an 8-bit register. Uh, this is an accumulator. As you can see, the accumulator is directly connected to the ALU. The ALU is the arithmetic logic unit, which performs all the arithmetic and logic related tasks which the microprocessor need. And this is a unidirectional connection. The unidirectional connection means that the data can be transferred from the accumulator to the ALU, but the vice versa cannot be done. So the ALU generally performs like addition, subtraction, multiplication, division, which requires two operands, and one of those operands will be stored in the accumulator. And after the performance of the operation, the resultant will also be stored in the accumulator. Like let's see here, in the operations such as the addition, subtraction, multiplication, division, the accumulator holds one of the operands and as well as the result. The addition, one of the operands is loaded into the accumulator, the other operand is added to it. The accumulator then holds the result of the addition. Now let's look at where the other operand is stored. Let's look at the general process registers. These six registers are the general process registers, also called as GPRs, which are named as B, C, D, E, H, and L. Each register are 8-bit registers. There is a special property of general purpose registers, also called GPR, is that when when the operand is more than 8 bits, they can form the GPRs can form pairs of BC, DE, HL to form 16-bit registers to store the operand. Now, one of the operand is stored in the GPR and other operand is stored in the accumulator. When the ALU needs to perform the operation, they are called into the ALU, then the operation will be performed and again stored in the accumulator. There is special property of H and L that they can also act as a memory pointers. Uh, let us see an example to explain the accumulator and GPR by the following four instructions. Load, say suppose this all instructions are in the assembly language. Move ACC 0x005 means that the load the value of 5 into the accumulator. Move R1, where R1 is we are saying one of a register in the GPR. Load the value 3 into the general purpose registers R1. Add accumulator R1, add the value in R1 to the accumulator. Move result ACC accumulator, store the result from accumulator into the memory. Stack pointer. Below the GPRs, we have a 16-bit register called stack pointer. It is a very important register which holds the memory of the top of the stack element in the memory. Uh, let's look into this. If this is the stack pointer holds the topmost elements memory address, and also it helps in pushing, adding, and popping, removing the data from stack efficiently. Let us understand it more detailedly. When this, before the stack address was pointing to the stack pointer was pointing to the address of D, but when an element C was entered, the stack pointers will now point at the address of C. So the address has decremented. When the pop option was performed, the stack pointer, which was initially pointing to the address of C, when pop was performed, it will now point to the address of B. So there is an increment in the address. Program counter. Program counter, below the stack pointer we have the program counter, which is also a 16-bit address. It will hold the address of the next instructions which will be performed by the microprocessor. We know that in an instruction cycle, first we need to fetch the instruction, then decode it, then execute it. But before we need to perform the fetch, we need to know the address where the instructions is lying, and that instruction's address is stored in the program counter. With the help of program counter, when we fetch the address of the instructions, the address in the program counter will be incremented so that it stores the address of the next instructions which needs to be performed. uh, in instruction cycle, it follows three steps: fetch, decode, and execute, and particular instruction. So to start the cycle, we need to fetch. And to fetch the instructions, we need the instruction address, and this address is stored in the program counter, which is also referred as PC. Increment and decrement register. Below the program counter register, we have another 16-bit register called increment and decrement address latch or register. We have seen in address, stack pointer and program counter that we have several cases where we need to increment or decrement the address of the instructions which are stored in it. These are performed with the help of increment and decrement address latch. Temporary registers. It is an 8-bit register which is located aside the accumulator. Here is the temporary register. It is represented by W and Z. Um, so there is a slight difference between the temporary register and GPR. In case of GPR, the programmer has a complete hold of the GPR and could manipulate the data in it. Whereas temporary register, the programmer can't access what's in it or manipulate in it. Only the microprocessor has the full access to the temporary registers. When an ALU operation is performed, one operand is stored in the accumulator, other operand is stored in GPR, which is later transferred to the temporary registers. And we know that the temporary register is connected to the ALU. So one operand is data goes to the ALU, and from accumulator, another data goes into the ALU where the operation is performed, and the resultant is later again stored into the accumulator. Arithmetic and logic unit. This is one of the most important component of the microprocessor, which performs the following operations such as arithmetic operation, which has operations such as add, subtract, multiply, and divide. Logical operations, which means bitwise or bitwise and complement, XOR operation, comparison operation, like the name suggests, it compares the values between two bits. Rotate operations, right, rotate left, rotate right. ALU is it performs all the arithmetic and logic related tasks which the microprocessor needs. This is the schematic diagram of the ALU which is present in the 8085 microprocessor. Instruction register. We saw before in the program counter that in an instruction cycle, first an instruction to perform an instruction, first we need to fetch it, then decode it, then we can execute it. To fetch the address, we use the help of the program counter. Now we have the instruction in hand. This instruction is stored in the instruction register. Here is the instruction register, which is an 8-bit register. Uh, It's an 8-bit register. It's a crucial component of the microprocessor which temporarily holds the opcode of the instruction that is currently being executed. The instruction register is an internal component of the microprocessor and is not directly accessible like by the programmer, just like the temporary register. In an instruction cycle, first we fetch, then decode, and finally execute the instruction. To fetch the instruction, we use the program counter like we seen in the program counter case, which has the address of the instruction stored in the memory. Now the instruction has been fetched. The address in the program counter is incremented by 1 and the instruction is traveled through the bus and is stored in the instruction register. When the instruction is stored in the instruction register, the fetch operation has been completed. Now the opcode is loaded into the instruction register. It is set into the instruction decoder, which we'll see in the next slide. Instruction decoder. This is located just below the instruction register, which performs the decoding task of the instruction cycle. In the instruction cycle, next is the decode, which is performed by the instruction decoder. Instruction decoder is a crucial component and plays as responsible for interpreting the opcode fetched from the memory and generating an appropriate control signal to execute the instruction. Based on the decoded output, the instruction decoder generally generates a specific control signal. The signals direct various parts of the microprocessor, such as the arithmetic logic unit, registers, and memories, to carry out the required operations. Flag registers. Uh, And this is the flag register. It is an 8-bit register. Once let's look into the diagram of the flag register. This is the flag register bitwise, and it plays an important role in microprocessor by giving us the status of the result operand operated after the operation performed by the ALU. As you can see, D1, D3, D5 are empty, which are not required and are not of any use to us. The flag registers has mainly uh, carry flag, uh, parity flag, auxiliary carry flag, zero flag, and sign flag. Let us look into the what is the purpose of each one of these bits, and let us understand in detail. Carry flag. Let us look into this example. When then addition is performed, when in the MSB addition, if a carry is generated, the carry flag stores 1. If not, then it will store 0 in it. Parity flag Parity flag, as the name indicates, if the number of ones are odd or even, it will generally set 1 or 0 accordingly. If the number of ones is even, then it will set as 1. If number of ones in the result is odd, it will set as 0. In the auxiliary flag, let us look at an example to understand the auxiliary flag. This is called the lower nibble. The last 4 bits are called lower nibble, and the first these 4 bits are called higher nibble. When there is a carry generated between the lower nibble and higher nibble, then the auxiliary flag will be set as 1. If not, it will be set as 0. Zero flag. As the name suggests, if the result is 0, it will set as uh, if the uh, if the result is 0, it will set as 1. If it is not, it will set as 0. And lastly, the last MSB bit is the sign flag. As the name suggests, if it is set as 1, it will indicate that the result is a negative number. If not, if it is set as 0, it will indicate that is a positive number. As set 1 is the most significant bit, result is 1. The result is negative in two complements representation, clear 0. If MSB is 0, the result is positive or 0. Uh, let's look at the summary of the flag register. If carry is generated, then CF will be 1. If odd parity, then P is 0, else P is 1. If auxiliary carry is generated, then AC will be 1. If the result is 0, then ZF will be 1, else ZF will be 0. If the result is positive, then SF will be 0, else SF will be 1. Timing and control unit. The timing and control unit generates the timing and control signals which are necessary for the execution of the instruction. It synchronizes all the registers and flow of data through various registers and other units. As my friend Pranav explained before, it has 16 pins. Uh, 16 pins are attached to the timing and control unit, which are the power supply pins, clock signals, control signals, data signals, DMA signals, reset signals. Each of the respective pins are mentioned here and has been explained by my friend previously at this part. This is the time.
Hello everyone, I am Abhinav. Now that we have explored the components of 8085 processor, let's talk about these components communication with each other and with their external memory through the bus system. We can think of bus system as highways that allow data to flow between different parts of the processor. In the 8085 microprocessor, we have three primary buses: the address bus, the data bus, and the control bus. These three buses serve different roles in transferring information between the CPU, memory, and the input-output devices. Let's break down each of the buses and discuss them in detail. Now, the address bus, also known as the memory location selector. The address bus is like the GPS of the processor. The address bus is like the GPS of the processor. It's responsible for locating where in memory the data or instructions are stored. The 8085 processor has a 16-bit address bus, which means it can access up to 64 KB of memory. It's unidirectional, meaning information only flows from CPU to memory or input-output devices. The higher 8 bits, A8 to A15, handle specific address lines, while the lower 8 bits, AD0 to AD7, are multiplexed with the data bus. So when the CPU needs to find a piece of data, the address bus delivers. Now let's head towards the data bus. The data bus is where the actual data is transferred. Unlike the address bus, the data bus is bidirectional, meaning the data can flow from CPU to input devices as well as input devices to the CPU. The data bus is 8-bit wide, so it can carry 8 bits of data at a time. For example, when the CPU reads from memory, the data travels from memory to CPU along the bus. When it writes, data flows in the opposite direction. Now, the control bus, also known as the traffic manager. This coordinates how the data flows. It carries signals that tells the CPU or external devices what actions to perform. The key control signals are read, write, input output memory, and ALE. Read signal tells the memory or input output device to place data on the data bus for reading. Write. This signal tells them to write data to the memory or the input output device. Input output or the memory. This distinguishes whether the operation involved is a memory or an input output device. ALE. It separates the address from data when the lower 8 bits of address or data bus are multiplexed. Now let's see how the three buses coordinate. Each of these buses, address bus, data bus, and the control bus, must work in perfect harmony for the processor to function smoothly. This coordination happens through well-timed bus cycles. First, the address bus sends the location to memory. Then the control bus signals the operation type. And finally, the data bus transfers data in or out. Timing is everything here. For instance, when the address bus is transmitting memory location, the control bus sends the ALE, address/enable signal, to ensure the address and data don't mix up on the multiplexed AD0 to AD7 lines. This way, all buses work in sync to avoid data conflicts. Now let's see an example to figure out how actually the bus system works. Step 1 is fetching the instructions. The address bus sends the memory location where the instruction is stored. Once the address is specified, the data bus carries the instruction from memory to CPU. At the same time, the control bus sends a signal called read to tell the memory that CPU is ready to read the instruction. Step 2 is loading the data into registers. Next, we load the data into the CPU registers. Here, the address bus will point the memory location of the addition numbers, which is our example. The data bus transfers these values from memory to the CPU's registers. The control bus makes sure that the values are loaded into the correct registers by managing the flow of data. Step 3 is executing the addition. Once the data is in registers, the CPU performs addition. The control bus sends the necessary signals to trigger the addition operation inside the ALU or the arithmetic logic unit. After the ALU processes, the result is stored in the accumulator ready for the next step. Now the next part is storing the result. After the task is done, that is addition, the result is stored back into the memory. To do this, the address bus specifies the memory location where the result should be stored. The data bus then carries the result from the CPU's accumulator to the memory location. The control bus now sends a write signal to tell the system to store the result at specified memory location. Now I'll go through the summary of the coordination between the bus systems. To sum up, the bus system works in coordination throughout this process. The address bus helps the CPU locate memory addresses for instructions, data, and the result. The data bus is responsible for transferring all the data and instructions between the CPU and memory. Finally, the control bus manages, or we can say coordinates, the entire operation, ensuring the CPU knows when to read data, write data, or execute instructions. Together, these buses work as a communication network within the processor, allowing each step to happen in synchronization. Now I'll tell you the importance of the bus system. The bus system is essential because it clears a, a structured pathway for communication between the CPU, memory, and other components. Without it, the processor wouldn't be able to coordinate operations efficiently. It simplifies the design by reducing the number of physical connections between the components. The system also ensures scalability. New peripherals can be added to the bus easily without any significant changes. In summary, the bus system is the backbone that enables smooth data flow and ultimately efficient processing. Now, finally, I'm going to tell you the limitations of 8085 processor and the evolution of future processor. While the 8085 bus system is effective, it does have some limitations. Firstly, it can access only 64 kilobytes of memory, which is a significant restriction for modern applications. Secondly, the multiplexing of address and data lines can cause delays, since the same lines have to switch between transmitting address and data. Finally, the 8-bit data bus limits how much data can be transferred at a time, affecting overall speed. As processors evolved, so did the bus system. Modern processors have much wider address buses, allowing them to have gigabytes of memory, and the data buses have also expanded with 32-bit or 64-bit buses, allowing much larger chunks of data to be transferred in a single cycle. Moreover, dedicated buses for memory and input-output operations reduce bottlenecks. Technologies like hypertransport and PCLE allow for even faster communication between the components. So as we move towards more advanced processors, bus systems are becoming more efficient, eliminating the limitations of older architectures like the 8085. Thank you.